Hello, my name is Andy Schweitzer, and this is a short video on composition of mass and composition by quantities. Some of the things we'll talk about here are going to be ratios of individuals based on formula, ratio of mass based on formula. We're just getting towards the end of bonding. We've seen things bonding together, and we're going to try to introduce some concepts that we'll see later on that can be used right now. But at this point, let's take a look at what I mean by ratios of individuals. So if we were to take, for example, NaCl versus, let's say, AlCl3, or let's go C6H12O6. All right, we have three different substances here, and you should realize that these subscripts represent the quantities of atoms present in each of these substances. This is 1 sodium for every 1 chlorine, 1 aluminum versus 3 chlorines, 6 carbons, 12 hydrogens, and 6 oxygens. These subscripts give you the quantities of these individual atoms, and they are locked. So no matter what you have, if you have one itsy bitsy little crystal of sodium chloride, you're going to have 1 sodium and you're going to have 1 chlorine. Again, this is a bulk crystal, but if you literally had 1 cation, 1 anion, this is what you'd have. So regardless of the sample size, I could have a small sample size or a very large sample size of sodium chloride. Again, you'd have 1 cation, 1 anion, 1 cation, 1 anion, 1 cation, 1 anion. Because this is locked, the proportions for the entire size are still locked. I could take this and divide up all my sodiums into one pile, and I could divide up all my chlorines into another pile, and even though my drawing isn't exactly the same, these would be equal. All right. Same thing goes for here. I have 1 aluminum and I have 3 chlorines. Now that's a little bit different ratio, but that is going to be holding true no matter what sample size you have. And that's very difficult for some students of chemistry to understand. That if I have 10 of these guys here, okay, that means I have 10 aluminums and I have 30 chlorides. Same portion, 1 to 3. 40 total or 4 total. If I have 100 of these guys, I'm going to have 100 aluminum atoms, and I'll have 300 chloride ions. So that is holding true. Let's look over here at glucose now, a little bit bigger molecule. These are both ionic, hence the empirical formulas. This is a molecular formula, but it doesn't really matter. There's 6, 12, and 6. So no matter what, 6, 12, 6 would be holding true. If you were to blindly analyze this chemical, you would see that it is showing up in a 1 carbon for every 2 hydrogens for every 1 oxygen. That's the ratio you'd see. This is the empirical formula. This is the molecular formula. Notice that the proportions are still the same. 1 to 1, 1 to 1. Either way, no matter what, this is whether it's on this level or on this level, it doesn't really matter. If I have 100 glucose of these guys here, I will have 600 carbons, I'll have 1,200 hydrogens, and I'll have 600 oxygens. So no matter what, my carbon and my oxygen would always be the same. They have to be the same. And the hydrogen will always be double the carbon and the oxygen. This would be true whether it's 100 or whether it's 1,000,000 or whether it's 10 billion. Okay. So if I have, let's say, for example, 1,000 of these guys, and the math just gets fairly simple, but 6,000 carbons, 12,000 hydrogens, and I have 600 oxygens. Okay, so these ratios are locked based on the formula of the chemical reaction. Now, how does this relate to mass? Unfortunately, it doesn't really work that easily. We have the mass versus quantity. Now, everything has its own mass, and that's what's unfortunate about this particular item. For example, in glucose, we have 12,000 hydrogens. Does that mean every single molecule of glucose, the majority of the weight is due to hydrogen? It might look that way, 12,000 of them, and then we have 600 carbons, 600 oxygens. Well, the problem is that each item has its own weight. Every atom weight has a different mass. So the question might be, is an atom a brick or is it a feather? There's always the common joke, if you have 1,000 pounds of bricks and 1,000 pounds of feathers, which one do you have more of? Obviously, the answer is or which one weighs the most? Well, they both weigh the same, but you have a lot more feathers. That's kind of where we're at on this thing here, is that if you don't know how much things weigh, you could look at an example of a molecule like C6H12O6, C6H12O6, and assume that you have majority of the mass being hydrogens. That's not the case. Hydrogens are feathers. These guys are relatively heavy. So how do we assign masses to these individuals? And we're going to do that strictly off the periodic table using atomic mass units, or AMUs. The atomic mass of carbon is 12. Now, if I go just plain old 12, we're assuming that this is 6 protons and 6 neutrons. Of course, we know the number of neutrons can vary, so they say 12.01 takes into account some of the average, that some are a little heavier, some are a little lighter. Then we're going to multiply that times 6 to get the total mass of all the carbons inside that particular molecule. And then this guy is 1.00 times 12 for a grand total for all the mass attributed to the hydrogen. And then the oxygen is 15.99, and for simplicity's sake, I am going to use 16. One 6.00, and we'll multiply that times 6 of them. So take a moment, and we will add up all the masses of these individuals. 12.01 times 6 equals 72.6. This guy is 72.6. That's be 0.06. And then this guy is just going to be 12.0. And then this guy is going to be 16 times 6 equals 96. So if we have one whole molecule of this thing, it's going to weigh 180.06. This is often referred to as its molecular weight. Okay, that's how much one molecule weighs. Now, of this 180, that's all these parts combined, this big molecule glucose, how much of this mass is due to the hydrogen? Okay, like we had said, there's a total of 24 particles here, grand total, 24 particles, 6, 12, and 6, that's 24. But what percentage of the actual mass is due to the hydrogen? Okay. Now, to do this, we're going to use the formula percent by mass. Now, this is going to be equal to the mass of X divided by total mass times 100. Okay. This is this proportion between the mass of the hydrogen and the total mass is a ratio that's locked because it's 12 to the total weight. The weight of the individual atoms is not going to change. The proportions of the atoms in this molecule is not going to change. So that means the ratio of the mass of the hydrogen to the total mass will not change either. So this fraction, or this ratio, or this relationship is locked for all sample sizes of glucose for all eternity. It's never going to change. So this will be 12 is the mass of the glucose located right here. Total mass would be 180. Okay, and we'll divide that out, and then we just multiply it times 100 would give us, well, we'll just do the math first here. 12 divided by 180 says okay. We have a value of times 100 is 6.667%. Now, in this case, this is our actual ratio, and that ratio could be 2 molecules be 24 over 360, same proportion. What this does is it multiplies times 100 and says, okay, if we have an imaginary sample of 100, what would we be? That's all percent is. Percent is an imaginary example of 100. If I have 100 grams, 6.66% of that, or 6.6 grams of it would be due to hydrogen. So even though over 50% of the particles, 12 of the 24 particles are due to hydrogen, only 6% of the weight is due to hydrogen. All right, well, let's do all the rest of these here. We got 72, this is for the carbon, and we have the hydrogen is done, carbon, oxygen, divided by 180 times 100 is, this is going to be pretty close to an even 40%. And then all my percentages should up to 100. You could subtract this off 100 to get this guy, but we'll just do the math here again. 96 divided by 180 times 100. And this is giving me a number of about 53.33%. Of course, all these guys are going to come awfully close to 100%, not exact. Okay? This tells me that no matter what my sample size, 53% of it is going to be due to hydrogen. If I had a 100-gram sample, it'd be 53 grams. This would be oxygen. Sorry, I misspoke. Either way, this is the percentages for any sample size of a mass. Here's an example. If I have a 5-gram sample of glucose, what are the individual masses of each one? Now, I can just go like this. There's a lot of ways to solve this. I'm going to use a ratio for this guy. And I'm going to go 5 grams over X weight. Okay, now this is the total mass. This is the mass of what I'm looking for. Let's say either hydrogen, carbon, or oxygen. And let's just use a little proportion. Okay, and you could say, okay, well, if I have 100 grams total, 6.66 grams would be due to hydrogen. Okay, but cross, multiply, and divide. This will give me my mass of my hydrogen in the 5 grams. So 5 times 6.667 divided by 100, and we get 0.333 grams. Now I could repeat this again. 5 grams over X equals 100 over, let's just say, 40. Okay, now I have the 100 on top, 40 on the bottom. I could reverse this. Doesn't make a difference. I go X on top. Cross, multiply, and divide. 5 times 40 divided by 100 equals, okay, 2 grams. All right, so that means X equals 2 grams. At this point, this would be for the carbon. My oxygen would have to then be 2 plus 3.33. Equals 2.333 minus that from your original 5 grams, and you get that the oxygen is going to weigh 2.667 grams. So this means that if you were to have a total of 5 grams, you could possibly extract 0.33 grams of hydrogen, 2 grams of carbon, and 2.66 grams of oxygen out of that 5-gram sample. Percent by mass. This is a fairly important formula right there. A couple things just to recap. You should be able to determine your percentage by mass, and then given, if you're given a percent by mass, you should be able to determine actual percent. So just a quick little review. We did an example previous, and that's it. Thank you very much.